Well, welcome back to our lectures here. We're going to finish up chapter 33 today by looking at inductors. And I'm going to put the inductor, after we talk about what it is and how it works, we're going to take this inductor and we're going to put it in two circuits. The LC circuit, which is an inductor and capacitor together, and the LR circuit, which is an inductor and resistor together. So we're going to see some similar physics that we've seen before. I think you remember the RC circuit back from, I want to say that was chapter 28. We talked about the RC circuit there. So the inductor, the LR circuit, is very similar as well. But first, let's talk about what this inductor is. Okay, so an inductor, well, let's start with a solenoid, right? We looked at a solenoid before. So we have a solenoid here. Okay, and let's say I have a current going into the solenoid on this left side here. We have a current going in like this here. Okay, so that's my current I. And it's kind of hard to see in this picture here. Let me see here. That how the wires are. So the wires, I'm gonna have a different setup here. So a different way of drawing this. So I'm gonna have these circles here. These circles are going to represent the top of this wire. I'll do that in black. So I have my circles here. Okay, so these circles are representing the top of my solenoid here. So that's this part here, right? This top part. These circles represent the top part of that wire, or the top part of that solenoid. And I'm going to do another set of circles down here. So let me draw that, representing the lower part of that solenoid. So these circles here. Okay, so we have our circles, and then now let's look at this current. The current is coming up, and let's say as it kind of goes to the top part of this coil, it goes into the page, and then comes out of the page, into the page, out of the page, and then into it, and then out of it, okay, and then into it. All right, so the top parts here represent the current going in, so I'm going to represent that with an X here, going into the screen here, so X. Okay, and on the bottom we have the currents coming out. So I'll put a little dots here. Okay, so that's our solenoid. We have the direction of current going through these coils, right? So you could also imagine, if you want to see it in this picture, going like that, right? Where that red arrow indicates is going in. Actually, let me do it. So currents will be actually going like this, coming out of the page here. Right, so that's why I draw it like this here on the bottom, because it's a lot easier to see that here than it is up here. Okay, so current's coming out of the page on the bottom here. All right, so if that's the case, what direction is magnetic field going here? Well, if we have our loops where the current is coming or going into the screen here, coming out of the screen on the bottom, right? If you do the right-hand rule, what you see is that magnetic field is going to the left, right? So I have all this magnetic field going this way here. Okay, so this is my magnetic field B. And I could draw the same picture or same arrows up here, right? Magnetic field going this way. Right. So this is magnetic field from a solenoid. Okay, so before I change anything, let's just stop there and see what we remember about this. We have talked about what the magnetic field of a solenoid is, right? The magnetic field of a solenoid is this here. Magnetic field of a solenoid equals mu 0 capital N, where it's the total number of turns times the current over the length of the solenoid itself. Okay, and what we're gonna not just use a magnetic field of a solenoid, but we also want the flux going through the solenoid. So we do have flux, right? You can think about it this way, that we have all these circles here. Let me see if I could highlight it here. All these areas, this area, right, this area, all these loops make areas, and then we have magnetic field going through those areas, right? So we do have a flux here, and we actually derive this. Let me erase this here. We actually derived this earlier. Whoops. We got for the magnetic field of a solenoid. I think it's one of the first lectures in chapter 30, chapter 30 here. N squared A over L. Okay, I think earlier I said that this chapter is chapter 33. This is chapter 30. Yeah, I'm stuck in the third edition of our textbook. All right, so chapter 30 here. So earlier in chapter 30, we talked about the flux from a solenoid. It's just really just doing, remember, flux is just B times A. All right, and we have multiple terms there, so we got to multiply it by N. So you plug in B into that, and you get your flux from a solenoid. Okay, so here's what I'm going to do with this. I have a solenoid, right? This is nothing new. We talked about this before in chapter 29 when we looked at the solenoid. I'm going to start changing my current. So now I'm going to say current, let's say it's increasing here. So I is increasing. What's current going to do? If that's increasing, what's going to change in my picture here? Well, what's going to change if I is increasing, your magnetic field is increasing. All right, so let me put that here. So B increases. Okay, so we have B is increasing, and also flux is increasing, right? Go back to our equation for flux, right here. So if my current increases, my flux increases. And that tells us a lot, right? As soon as we start to see that flux is changing, Faraday's law should come into play, right? So if our flux, as the flux begins to change, flux. Okay, so this is what Faraday's law says, right? If your flux is changing, you're going to get a voltage that comes out from that. So let's apply Faraday's law here. So Faraday's law says, I'll put it right here like this. Okay, so that's Faraday's law. And so we could plug in here our equation for flux. So flux is mu 0 n squared A over L I. Okay, and then this is what we get. So the d over dt there, let me make that a little bit neater here. D over dt. Okay, so we're going to take a time derivative here. What's changing as a function of time, right? What's changing as time continues? Well, there's not all these, I have all these constants here that do not change, right? Mu 0 n squared A over L, right? This is not changing. So I'm going to take that out of the integral, or out of the derivative, I should say. So negative mu 0 n squared A over L. And then I have di over dt. Okay, so all these constants here are just representing your solenoid, right? Or what we started, our inductor, right? Mu 0, n is just the number of turns, A is the area of that of the solenoid here, and then L is the length of the solenoid. So all this, we're just gonna bunch up together because all these are constants, right? All these are specific. Well, mu 0 is a constant for sure, but all these here, N, A, and L, are specific to that particular solenoid, okay, or to that inductor now. So I'm gonna, instead of having all those, I'm just gonna call it L. So negative L di over dt. Okay, so this L is what's known as inductance. Okay, so inductance here. And it's measured in something called henries. Usually we're looking at millihenries for a typical value for an inductor. So it's usually around that, or about a millihenry, like 100 millihenries or 80 millihenries, something like that. Okay, so that's just a value here. Okay, so let's look at that equation here. What we're saying here is that the voltage here across your inductor, across this, is negative L, right, some constant here, times di over dt. I want to try to make sense of this. I mean, that's our equation here, but how does that make sense? Why is it a negative here? What does the di over dt mean? Okay, so let's think about this scenario that we have. So I is increasing here. Okay, so I is increasing. which means magnetic field is getting stronger and stronger going to the left here, right? This is why I have this picture down here to see that, you know, if you do the right-hand rule, we do get magnetic field going to the left. So now magnetic field is getting going stronger going to the left. So if I'm getting more and more magnetic field going to the left, Lenz's law says that we're going to have an induced magnetic field going to the right, right? Remember, Lenz's law says that the induced magnetic field is going to oppose the change in flux. So my flux is increasing. You can see magnetic field there going to the left there. So my induced magnetic field will be going this way for each loop. Okay, this is my induced magnetic field, be induced. And that's going to give you a current that goes opposite of the red current. So we get an induced current, induced, going the opposite way. Okay, so now be careful here. I'm not saying that this induced current here is going to cancel out the red current, right? This red current and this induced current do not cancel each other out. Typically, this induced current is going to be a lot smaller than the red current. But what this induced current does is it gives a voltage difference. You can think of it this way: the induced current is almost like it's moving charges. Like you're going to have a buildup of positive charges here and negative charges on the left side. So it makes a voltage difference here. So this is what this is saying down here in our equation, that if di over dt, right, that rate of change is positive, in other words, it's increasing, this is going to give you a negative voltage, right? You get a voltage drop overall. The L here is just a proportionality constant. So it's just going to either magnify, magnify the effects of this. So if this is 4, then we're going to see 4 times the voltage change due to this change. If the L is 2, then we see 2 times, it'll multiply this by 2 to give us our voltage. So this is just really a proportionality constant there. But it really goes down to this, di over dt. If it's increasing, positive number, we're going to get a negative voltage, right? A voltage drop. If this is a negative number, right? In other words, if current was decreasing as a function of time, then this will get a overall my voltage will be a positive number, right? This will be a negative times a negative will give me a positive overall. Okay, so kind of interesting there. That inductor, once we putting a solenoid by itself doesn't do it, but as soon as current starts to change, then we start to see those differences. Okay, so something really interesting happens when we not just because of this, but let's look at it from a perspective of energy. Okay, so let me go over here, draw my solenoid again. Put this there. Okay, so we're going to have our inductor here. Okay, there's our inductor. And, let's look at the same picture that we had earlier. So we have current here going up. We could say current is increasing. Okay, what about energy? Let's start with power, actually. So let's look at power. If I look at power, one of the equations we looked at before is I times V. Okay, so we use that equation when we looked at resistors, that I times V will be how much energy is lost in the resistor, how much energy is lost by the resistor, I should say. But now we're looking at the power in an inductor. And inductors do not lose energy. We don't have any kind of resistance in here that's dissipating energy in the form of thermal energy like we do with resistors. In an inductor, they store energy. So that's one big difference when we talk about this power. So when I talk about power, and I'm going to plug in I. Well, I is just I. And my voltage is negative L di over dt. Whoops. Okay. I'm gonna use this equation to get energy. Now power is d. Remember what power is. Power is just how much your energy is changing. Is a rate of change of your energy. So du dt is what I'm going to have here. And I'm going to have I, and I have negative L di over dt. Now we kind of have to think about what we're actually calculating here. What we're calculating is the energy change over time. Okay, so if I is increasing here, magnetic field is getting stronger. We're not losing energy there, and I'll show you guys this in a second. I have a little simulation I'll show you. We're not losing energy. What we're doing here is gaining energy. So I shouldn't have this negative here. The negative will mean that I'm losing energy over time. We're actually gaining energy. So you can think of this as just looking at the absolute value of voltage. I'm just going to make this positive then. Okay, so we don't want the negative there, because the negative would again tell us that we're losing energy, which is not true for the inductor. The inductor is storing energy. Okay, so let's get our equation for you. So I'm going to take this dt to the other side. So I have I, L, di. The dt's cancel out, right? Dt's go away. So this is what I'm left with. And we're going to integrate. Right, we're going to integrate from 0 to some value of I. Right? If it starts from 0 current and goes up to some value for current, 2 amps, 5 amps, whatever it is, what is the total energy that this inductor stores? So U, right, the integral du becomes U. And on the right side, the integral IL di becomes 1/2 L I squared. So that is my energy for an inductor. It's storing energy. And it kind of looks similar to something we've seen before. Let me show you. Remember this equation? Okay, so you remember this equation here? This is the equation for the energy in a capacitor. So you compare the two, right? You have so let me actually notate that here. This is energy in a capacitor. So energy in a capacitor here. And again, this is the energy in an inductor. Okay, so there is a difference, right? One has L, one has C. The other one depends on current, while the capacitor depends on voltage, but very similar form. And what we're going to see in a second is that, and we could probably even show this here, but the energy in an inductor is stored in the magnetic field, right? Current here, as the current is flowing through it, it's giving you a magnetic field inside the inductor, right? So that magnetic field is giving you that energy. For a capacitor, we saw it's not so much just voltage in itself, but in a capacitor, let me just draw a quick capacitor over here. Let me just draw that capacitor. That voltage is there because you have an electric field. It's going in this direction. So in one case, the energy is stored in the electric field. On the other case, for the inductor, energy is stored in the magnetic field. So they're kind of working very similar in the fact that they're using these fields to store energy, but they're obviously different kinds of fields. Okay, so that is an inductor. So what I want to do with this inductor is take the inductor and put it in the same circuit as a capacitor. Okay, so this is what's known as the LC circuit. Okay, so pretty simply, here's how an LC circuit looks like. It's just really a capacitor attached to an inductor. So looks something like this. That's my symbol for my inductor here. So on the left side, I have my capacitor. On the right side, I have my inductor, and we just put an L for inductor. And I'm going to start off with my capacitor charged up. Okay, so I have charge here. There's a positive charge on one end, negative charges on the other end. Okay, Okay, so I want to know what happens. Let me actually do this here. Let me put a switch in here because I want to have a switch. Oopsie. So I'm gonna have the switch open for now, right? It's not closed. So with the switch is open, right, that nothing's gonna happen. That charge is gonna stay there. It's not gonna move. So when I close the switch, after I close the switch, what is going to happen to this circuit? So actually, okay. So I want to, before we talk about it, I want to show you the simulation here. I have a simulation. Let's see the inductor capacitor. Here it is. Okay, so here's my simulation. Right now, nothing's happening because I have those switches open. So I have my battery right here. Okay, that's my battery, my capacitor, and then my inductor. Okay, so I'm gonna close my switch here, this one, and all that switch is gonna do is connect the battery to the capacitor. So the whole point of that is just to charge up the capacitor. So let me charge up my capacitor. There you go. Okay, you see that quick flash of fire. It just means that the animation went so quickly that I couldn't keep up. Okay, so but it essentially instantly charges my capacitor. All right, so I'm going to open this now. So now the battery is not involved at all. Right, the switch is open. Battery is on its own. So now I have my charge here, and this inductor, right, connected to each other. And as soon as I close the switch, let's see what's going to happen. Close. There it goes. Okay, so you can see the charge starting to move there. A loose charge, but then I'm having current, and it kind of, we're going to see a polarization, right? A different polarization. Now I have negatives on top, positives on the bottom, and that current starts to move again. And you know that it keeps, what we're seeing here is an oscillation, right? Look at the charges. The charges keep changing. I wish I could make this a little bit faster. I probably can by changing the values here. Actually, let's do that. Starts off slow, but it should pick up speed here. Okay, yeah, wasn't that much of an effect. Anyway, yeah, so this is what we're seeing is that the polarization of the capacitor keeps flipping, right, going from positive to negative, and the current going through the inductor increases and decreases. So actually, let's look at this current. So I want to have, not voltage here. Let's look at a current. Okay, so I'm going to bring this right over here. I just want to look at what's happening to current. You know what I could do to make this? I just totally think about this. I could let me increase my voltage. That's probably a lot better. Change voltage here. Well, kind of go crazy there, but let's see. Open that, close this, charged up, and then close this. There we go. That's what I wanted to see. A little bit better animation here. Ugh, maybe I put too much. Look at that. There it goes. Okay, so let's look at this current for a second. Current is negative now. Now it's zero. It's going up, coming back down. And you know, if we keep looking this over time, you're going to see kind of a similar shape here. What does that shape look like? It's essentially a cosine sine curve, right? It goes down, reaches zero, goes back up. All right, so we're kind of seeing this sinusoidal behavior with the current, that the current is fluctuating, going up and down, just like a sine curve. And I want to stop this animation at certain points here. So let's stop it when this is zero current. Okay, so zero current will be right about here. Okay, so I paused it. So zero current. So zero current means I have no energy in my inductor, right? Where is all the energy? The energy is in my capacitor, right? So because you can see the capacitor is fully charged. Now let's look at when we get max current. So when we get max current, following that line there, going to reach some maximum value. Okay, so let me do this. That charge goes to 0 pretty quickly. There it is. Okay, so now it's just okay. So pretty much 0 charge on my capacitor. Let's just say 0. I know you can see some charges there, but it's supposed to be 0. So 0 charge, and look at my current. In my inductor, current is maximum. So think about what's going on with energy. Now I have maximum energy in my inductor, minimum energy in my capacitor. So as I keep pressing play here, all we're seeing is that the energy from the capacitor and the inductor is just bouncing back and forth. Right, it starts off with energy in the capacitor, goes to energy in the inductor, and then vice versa. The energy in the inductor then gives up its energy and then goes to the capacitor. So it's kind of an oscillation, if you will, between energy going from one to another. Now that's really important because what we're going to see here when we start analyzing it. Let's see. Let's go back to the whiteboard. Well, what we're going to see here when we close it is exactly that. It's just oscillations. So now I'm going to close my switch here. And we know what we expect to see, right? Once I close the switch, charge is going to be moving. But let's look at it mathematically. So if I make a loop here, let's do a loop law here. Here's my loop. Loop law says that VC plus VL. So voltage across my capacitor plus my voltage of the inductor equals 0. Okay, that's going to be true no matter what time you're looking at this. No matter where how much charge you have on the capacitor, no matter how much current you have in your inductor, this is always going to be a true statement here. Okay, so let's see here. So what can I plug in for VC? VC is Q over C, right? VL, well, VL, it says negative L di over dt. Right, this is the equation we got for the voltage across the inductor from our previous slide, right? That's or 2 slides ago, right here, right down here. Okay, so that's a voltage across my inductor. So that's what I plug in here. And when I look at this Q and I, so I have I right here, which is the current going through the inductor, and Q, which is a charge in the capacitor. These two are related, right? Where is this current coming from? This current is coming from the charge being lost in your capacitor, right? The capacitor is giving up charge and going into your inductor. So these two are related here, and it's related specifically by this equation here. So I, well, we know I is just dq over dt. But if Q is the charge in the capacitor, in order to have current, the capacitor has to lose charge, right? Q has to be decreasing. So in order to take into account that decrease, I'm going to put a negative there. So that the current equals the negative change in charge from your capacitor. So take that and plug it in here in our equation, in our loop equation. So Q over C plus, I lose that negative and I get L d squared Q over dt squared equals 0. Okay, so let me rearrange this and let me see. So rearranging it so that d squared Q over dt squared is by itself on the left side here. I get let me see, negative L over C Q. Now that should look familiar. Maybe it doesn't. Maybe some of you are not in the at the point of your physics mastery where you can see that equation and recognize it. Let me show you a similar equation that you've seen before in your previous physics class. So let me write this here. Let's see. Okay, so so does that look familiar? Right, that equation here. This is the equation for the simple harmonic motion of of a spring, right? So the let me put here. Simple harmonic motion of a spring. Right, and remember for a spring, the spring is just essentially changing energy from potential to kinetic, right, and back and forth. Imagine if I just really quickly here draw a spring and have a mass here. That mass is oscillating back and forth, back and forth. And as it does that, it goes, if you think about energy, it goes from kinetic to potential, right? It has that oscillation, if you will, of kinetic to potential and then potential to kinetic, right? It keeps going on and on and on. Well, that's essentially what we're seeing here, right? With the LC circuit. It's the same equation, right? Compare that, the blue equation that I just boxed here, to the black equation right under it is very similar. You have a second derivative on the left equals a negative constant, right? In this case, L over C, and then times Q. So if we solve this differential equation, and we're not going to do that here because I think some of you haven't taken differential equations yet, which is fine. We get this equation for Q. So this will solve the differential equation here. So Q max cosine omega t, right? Gives us back that cosine wave that we were seeing earlier. What would be omega? So omega is just a square root of, oh, I did my math wrong. Did I do my math wrong? Let me see here. So right here, when I bring this over to this side, I should divide by L. Ugh. Algebra. Make sure I get that right. There. I think that's, let me double check one time. So negative Q over C and divide L to both sides. Yeah. All right, so that makes more sense. So 1 over LC is our omega there. Yeah, if you remember, whatever your constants are here, that's essentially your omega squared. Okay, so we get an equation for Q, right? This charge on the capacitor is going up and down, just like we saw, right? Increasing, decreasing, and vice versa. And we could find I, right, the currents through the inductor by the equation we had earlier, right? Negative dq over dt. Okay, well, we have Q now, right? This is our Q. So I take this Q and plug it up in here. And so let's see, we take the time derivative of Q, which is just going to be I max. So let me actually just go slowly. Let me just take the derivative. So if I take the derivative, I get Q max times omega, and cosine, the integral of derivative of cosine is sine, negative sine, so sine omega t. So this sign out in front, or this negative here, should go away. When you take the derivative of cosine, you get negative sine, and so that would cancel out this negative out here. So here's our equation there. And Q max times omega, if you just look at the units here, this is coulombs. Omega has units of 1 over seconds. So coulombs per second. And what's a coulomb per second? So what we get for our current here, I max times sine omega t. So kind of essentially verifying what we observed. Q, the charge, is a cosine function, whereas I is a sine function. So these two are essentially out of phase. When charge reaches its maximum, current will be 0. And when current reaches its maximum, charge would be 0, right? Because one's a sine function, one's a cosine function. So essentially verifying here what we saw. And in terms of energy here, we don't have kinetic to potential in our case. What we have here is 1/2 Li squared, right? Energy in our inductor going to our capacitor, and then vice versa, right? So it's energy going from one to the other. All right, let me put it in terms of charge here, right? I could put this in terms of charge, right? Q over C squared, or Q squared over C. Okay, so this one depends on current, This one depends on charge. So when current is maximum, you have maximum energy. And then when charge is zero, you get zero energy in your capacitor, and then vice versa. So energy just keeps bouncing back and forth here. Okay, so kind of, it's kind of interesting that we see that the energy is being stored from electric fields within the capacitor to magnetic fields in the inductor. So kind of interesting there, that you wouldn't expect that just by connecting those, but that's what we see. Okay, so let me do one more circuit here, and that is the LR circuit. Okay, LR circuit. So the LR circuit, let me do a quick setup here. So it looks something like this. We're gonna have a battery, and we're gonna have this this junction here. All right, so we have a battery, and I'm gonna have this junction here that goes to a resistor, and now it goes back to the battery, and then a inductor. L, R, this is my battery, so I'll put V here. And the switch here, the switch could go from the just connecting the resistor here. Actually, no. Oh, this other. It could connect to the battery, or it could connect to the resistor, right? So either we have the inductor and the voltage together, or they have the resistor and the inductor together. Okay, so that's kind of my circuit here. So let's analyze this circuit here, just the voltage and the inductor together, and let's see what happens. So let me actually have a simulation for this one as well. Let's go, let's see, inductor. Okay, so inductor. Okay, so here's my simulation. Actually, let me disconnect this here. I couldn't figure out a way to do this circuit here. Maybe you guys can, but the way I'm doing that junction there, I couldn't figure out a way to do it in my program. So I'm kind of cheating here, but it'll still work. Okay, so let me close this, and let's see what's happening once I close it. So it starts off pretty slow, right? It doesn't go immediate. Why doesn't it go immediate? Because of Lenz's law, right? Lenz's law is kind of keeping that current down, but you can kind of see the current starts to pick up. And the way I could explain this is just by looking at our equation for the inductor. So we said the voltage of the inductor equals negative L di over dt. Right, that was our equation. So what's going on with this circuit, if it's just connected to a battery and the inductor? Well, voltage here is staying constant, right? Voltage is whatever the voltage of the battery is. Let me press pause because it's gonna get crazy. Okay, so whatever I think the voltage of the battery is like 9 volts or something, right? So whatever the voltage of the battery is, that's gonna be the same voltage across the inductor. So this is staying constant. L is of course constant, right? It's just your inductance. Oops. Inductance of your inductor. And then so that means if VL is constant, L is constant, then di over dt has to be constant. Now think about what that means. If di over dt is constant, that's saying that current has to be increasing at a constant rate. And that's actually what we're seeing here. If I press play, current just keep going, getting faster and faster and faster, right? Eventually, I think we're going to start to see fire here because the animation can't keep up. So it's going to go faster and faster. Oh, there it is. But that's not realistic. Obviously, current just can't keep building. And the reason why it's not realistic here is because there are things in reality that this simulation doesn't take into account. For example, batteries have internal resistance, as we have learned. Let me press pause here. So if I put an internal resistance here, we won't see this current won't keep building and building and building. The internal resistance will essentially limit how much current could actually flow through this. All right, and also inductors themselves have resistance. In the simulation here is taking this inductor here to have 0 resistance, which is not true, right? If inductors are just made up of a whole bunch of wires wrapped around, like a solenoid here. So these wires have resistance in themselves, but we're ignoring that resistance here. So even though, this is what this equation says, that current should keep increasing, that's not necessarily a realistic thing that would actually happen. Okay, so let me reset the dynamic here. So I'm gonna press play again. Oh, you know what? Let me actually connect this time. I'm gonna press play. So all this does is I'm adding a current through the resistor. It's not really going to change our results. So what I want to do here is open this up. So I'm going to let this build. Okay, I'm going to let this build right here. Current is building and building and building. And let's get a current chart here to see what happens to current. You can see it's holding steady there at 1 amp, it looks like. I wish I could make this bigger, but I can't. And let's look at voltage. Now, current is holding steady there, but if I were to go to the inductor, it's off the charts here. Oh, I guess it's negative. The negative doesn't really, there you go. You can see current keeps increasing. So the current through the inductor is increasing. Current through the resistor is staying constant at 1. And there's a fire. Okay, so let me get my voltage here. And I'll put the voltage across this. All right, so things got a little crazy here, but you can see voltage is staying the same, right? 10 volts. So like I said before, voltage is staying constant because I guess my battery's at 10 volts. Oh no, it looks like 9. Maybe zoom in there. Right, it's just under 10. Okay, let me reset. This is getting a little too crazy. All right, so going back, everything down. The current goes back down to 0. It's going to start building, and you can kind of see it in the graph even starting to build. Voltage is staying the same, staying constant. Okay, so all I want to do is let this build up for a little bit, and I'm going to open the switch here. So when I open the switch, I'm essentially taking this here, the switch, and just moving it. Oops, moving the switch over to connect it to the inductor here. All right, and we're going to analyze that circuit. So let's go back to the simulation here. Okay, so let's open that switch. You can see my voltage is at 10. Current is right about at 5 right now. So open it. And look what happened to my voltage. Voltage essentially flipped, interesting, and went down to 50. And you can see what's happening to my current. Current is decreasing here. So kind of, weird. It is decreasing, so it's kind of a decay here. Current is eventually going to come to 0. Same thing with voltage. You can see that voltage. I could put a voltage right here. That voltage going down to 0. So unlike the LC circuit where we saw energy bouncing back and forth, here we're seeing energy being lost. And it's because of that resistor, right? That resistor is losing energy, dissipating energy in the form of thermal energy. Okay, so we're going to analyze it. Why is it that we start to see a positive voltage here, and when I open it, that voltage jumps down and becomes negative, right? And especially the more current I let build, the greater jump we'll see with that voltage. So right now it's at 9 volts. You can see my current slowly building, right? That has that linear increase in my current here through the inductor. And the more current builds up, the greater voltage change we're going to see. So it now goes down even further to negative 25. Okay, so why is that? So in order to answer that, we're gonna analyze this. So the second this flips over, we are already starting with a current through here. Okay, so I'm just gonna call this I. Okay, so let's set up my my loop law here. Let's see here. Do my loop law. And my loop law, if I do, it's voltage across my inductor plus voltage across my resistor, and that always equals 0. Okay, voltage across my inductor here. So this is negative L di over dt. And voltage across my resistor was negative IR, right? Voltage drop across my resistor equals 0. All right, so let me see. Let me rearrange this here. I'm gonna be careful with my algebra this time. And I'm gonna get the I, let me just go slow. Negative L di over dt here equals IR. And I want to bring the i's to one side of the equation and everything else to the other. So if I do that, I get di over I on the left side. And on the right side, I get, what, that L R over L, negative R over L dt. Okay, so let me double check that just to make sure. Yeah, it looks like that's correct. Okay, and now I'm going to integrate both sides here. All right, so let me start, finish this up over here. So the integral, let me put from I0, my initial I, to some final I, and this would be my initial time. Let's say time equals 0 initially, to some final time t. So when I do the integral on the left side, I get what would be ln of I over I0. I do that integral. And on the right side, I get negative R over LT. So, you know, we have a natural logarithm there. Let me take the, take it to the power of e to both sides here. And if I do that, the ln goes away. So I over I0. And on the right side, I get e to the negative R over LT. So solving for I, my current as a function of time here is going to be your initial current, I0, which we can find out what that is, e to the minus t, and I'm going to write it like this, L over R. Okay, the reason why I write like that is because usually you don't have L over R there. You'll see as a substitution here, instead of the L over R, you'll see it as tau, which is known as the time constant. And we actually seen this before, back when we looked at an RC circuit. Okay, so tau is just your L over R. Okay, so what this is telling us is that, let me make that a little bit better. Current will, I don't know if I could. Right. So what it's telling us is that current is we're gonna see an exponential decay in current, and how quickly that decays depends on L and R. So that tau is just telling you how many seconds it's gonna take to reach, what is it? Yeah, so one time constant tells you how long it takes to reach 37% of its initial electric field, oh sorry, initial current. Right, so so let's say that time constant was 10. That means 10 seconds from when we made that switch, it's going to be 37% of what it initially started with. So if I wanted to make this decay slower, right, make that current last a little longer, I would want there to be a lower R, smaller resistance, and a larger L. And that kind of makes sense in terms of energy. If I have a lower R, lower resistance, that means there's not as much energy being dissipated here. If I have a larger L, more inductance, that means I have more energy stored in this. Okay, so that is the LR circuit. So the LC circuit kind of bounces energy back and forth. The LR circuit, very similar to an RC circuit. The LR circuit is going to lose energy, and we see that decay. All right, so that's it. That wraps up our chapter 30 lectures. We'll stop here. Our next video, we're going to jump into chapter 32. So we'll skip chapter 31 for now. We'll come back to chapter 31, but the next lecture we're going to be focusing on chapter 32. So we'll do that next time.